Okay, back again. Chemistry 3202 course overview, Unit 1, Section 3, Lesson 1, the equilibrium constant, K. Here are the textbook sections for this material and some selected items that you might want to try for homework. We're looking at this equilibrium constant K. What does all this mean? Well, up to this point we've been looking at equilibrium in terms of reaction rates, where the forward rate equals the reverse rate. And then we were looking at it and saying, well, how do we know if something is in a state of equilibrium? And we said we looked at the color, and the color wasn't changing, or we could look at the energy it was producing. That was constant. There was no temperature change. Or the pressure of the system wasn't changing, and if gases were involved, the pressure of volume wasn't changing. We also looked at it and said, well, what if we start disrupting? What if we start adding a stress to the system to see if we can get it to shift one way or the other, depending on what type of stress we added? And that was Le Chatelier's principle. What we want to look at this time is a quantitative aspect of equilibrium. Can we quantify it? Can we put an actual number on it to say, how far one way or the other is this equilibrium? Because everything we've been looking at so far has been qualitative. It's a judgment call. Is the color changing? Well, it doesn't look like it's changing to me, but it may be changing slightly, but we can't detect it with our eyes. So things like that, it's all qualitative. It's a judgment call based on what you see. What we want to do is quantify it and put a number on it. And this number that we quantify equilibrium with is known as the equilibrium constant, K. So again, as we've been saying, up to this point we've been qualitatively looking at equilibrium. You know, what we can observe. The visual equilibrium, the fact that the color's not changing, the temperature pressure's not changing, the concentrations are not changing. And we know that we can start stressing this by changing any one of these situations, and the equilibrium is going to respond accordingly, depending on what type of equilibrium we have. What we want to do here, as we were saying, was to quantify the actual equilibrium position. We want to use numbers to try to explain which way it's going, how fast it's going, and how far. Remember we had that cat on the log? You know, if we give him a little nudge, how far can we push him to the other side? And could we quantify how far he's leaning to one side or the other? And that's what we're doing here. We want to be able to quantify how far the equilibrium is leaning in the forward direction, or if it's favoring the reactants, how far it's leaning in the reverse direction. So therefore, what we want to be able to do is we want to be able to predict the equilibrium mathematically. And then once we mathematically put a number on equilibrium, there's no argument as to how far one way or the other the equilibrium has shifted. So therefore, we can easily see that, you know, we've just witnessed a color change. All right. Well, how much is that color change? How far to the right has it shifted? And we want to be able to put a number on how far we've gone. Okay. In order to do this, we need to use something called the law of mass action, and this is what we would refer to as the equilibrium expression, and it's simply referring to the ratio of the product concentrations over the reactant concentrations. Okay, and I got a little bit of a mess made here, but let's just have a look at it. So the equilibrium expression is just simply a ratio of the products over the reactants. Now what we're looking at is these guys are the products on this side. So we're looking at the concentrations of, say, C and D on the top versus the concentrations of A and B on the bottom. Now you notice here we've done something a little different here. We're looking at this and we're saying it's the concentration of the products. The square brackets is representing concentration. The little c and the little d are the exponents of the concentration. Now this little c here comes from the balanced coefficient that would be in front of this equation. So for instance, if this equation was balanced 1, 2, 1, 2 like that, then the c would be replaced by a 1 and the d would be replaced by a 2, indicating that it would be the concentration of c to the power of 1 and the concentration of product d to the power 2. Likewise, In the case of the reactants, A and B, we would replace the A with a 1 and the B with a 2 down there. So that's what we refer to. We'll do a few examples here now. So in this particular example then, the equilibrium expression would be written as C to the power 1, D to the power 2, A to the power 1, B to the power 2. Okay? And that's what we refer to as the equilibrium expression. Okay, now this is going to be a constant. We refer to it as an equilibrium constant. It depends on the type of reaction we have. It depends on whether it's endothermic, exothermic, what types of reactants or products are present, and the degree to which the reaction is going to shift forward or reverse. So it depends, the size of K depends on what type of reaction we have. And we rarely put units on it, and we'll show you why now in a minute, why we rarely use units for this number. And the size of K, how big K is dependent basically on the temperature. Now temperature has to be held constant here in order for K to stay constant. The only time K is going to change its number is if the temperature changes. And again, we'll look at this in more detail now with a couple of examples. So K is a constant at a constant temperature. If you change the temperature, then K is going to change. If temperature remains constant, then K, the value of K, is going to be the same thing regardless of what pressure or what concentrations you start throwing in or whatever other stress you might do. So the temperature has to be constant in order for K to be a constant value. Okay, now a couple notes to go along here with this. Remember, solids and liquids do not change concentration. They are incompressible. We can't change their concentrations. Pure solids, pure liquids, they're already 100% pure. You can't make them any more pure than what they already are. You know, pure water is 100% water. You can't increase its concentration because it's already maximum. So if you're using pure solids or pure liquids in a chemical reaction, you never ever include it in your law of mass action here, the equilibrium expression. So therefore, the only things that you're going to include in this expression here would be the ones that are gases or aqueous, because that's the only ones that are going to change their concentration as the equilibrium shifts one way or the other. So if these guys are all gases, then fine, we would use them all. If they are all aqueous or gases, we would use them. If A happened to be a solid, then you would omit A from this particular mass action equation. So if A was a solid, then I would not include A in this equilibrium expression. Let me do an example to show you. So only solids and gases. So here we go. In the first reaction here, first equilibrium system, we're looking at let me just black out the rest of these guys. Okay, here we go. So if we're looking at this first system here, we're seeing that solid, gas, the reaction is balanced 3-3-1-3. So I'm looking at this guy and we're saying, hey, now this is an equilibrium system, so we want to write the law of mass action. The very first thing I'm going to do is say, okay, forget that guy because it's a solid. Let's forget that guy because it's a solid. So the equilibrium expression for this particular system is going to be K equals the products over the reactants. And in this case, the products are hydrogen, so it's going to be the concentration of hydrogen cubed divided by the concentration of water cubed. Now I know what you're thinking. I just said that if pure water was there, you wouldn't use it because pure water, the concentration wouldn't change. But that would be pure liquid water. In this case, water is a gas, and in that case, the concentration can change. Now, the equilibrium value for this reaction is given at 800 kelvins. That's very, very high temperature, 800 kelvins, and this constant value would be 12.3. Okay, so the value of K at 800 kelvins would be 12.3 for that particular reaction. Let's look at another one. Okay, here's another chemical equilibrium system, and we're looking at this guy and saying, okay, omit the carbon because it's a solid. And that's it. Everything else has to be used because these guys are all gases. So we're looking at this as an equilibrium expression. Remember, K is going to be the products over the reactants. And in this case, it's going to be the concentration of hydrogen to the power 1. We don't write the 1. The concentration of carbon monoxide gas to the power 1 divided by the concentration of water gas to the power 1. And this value is going to equal 10.0 at 1100 K. That's very hot. That's almost 800 degrees Celsius. Okay, here's another one. We look at this guy here now and we're saying, okay, this guy is a little bit different now because look at the state of water. Water is in the liquid state. So we're going to omit that guy because pure water cannot change its concentration. So we got to watch out for water here. That's very, very important. So in this case, the water crosses out because it's a pure liquid. The equilibrium expression, again, it's going to be K equals products over reactants. So in this case, it's going to be the products, which is CH3COOC2H5 to the power 1 divided by C2H5OH to the power 1 times the concentration of that acetic acid there, CH3COOH to the power 1. And this guy has a slightly different value. This guy is 0.11, so that's a lot smaller than what we've seen up above. And you can see that the temperature is 343 kelvins. That's about 80 degrees Celsius or so. And we're looking at this and we're saying, hey, the values are different. So the equilibrium position, where we're teetering from forward to reverse is going to be different in each of these cases because each of these guys has a different value for K. And the important thing here is that we're always stating at what temperature the value of K is representing. Because remember, K depends on the temperature. If we should change the temperature, if we had to heat this up to say 500 kelvins, then this value of K would change to reflect the change in temperature. All right, one way or the other. So K is temperature dependent. And finally, we look at this last guy right here, and we're saying, all right, all gases, these guys are all good to go. So in this case, we're going to look at this and we're going to say K is going to be products over reactants. So in this case, it's going to be the concentration, square brackets means concentration, of the methanol divided by the concentration of the product. So it's going to be the concentration of carbon monoxide times the concentration of hydrogen squared, right? Because we've got to take into account that squared there. And this guy has a different value. Again, this guy is 14.5 at 500 K. Okay, here we go. Now we have to look at this from the perspective of which way we're writing the equation or which way we refer to the equation, because remember, equilibrium is a situation where the forward rate equals the reverse rate. So it depends on what way we're looking at the equation. What are the products? If we're going in the forward direction, the products are nitrogen dioxide. If we're talking about going in the reverse direction, then the products are going to be N3O6. So it changes the scope of what we're doing. So what we're saying here is that we're relating the forward and reverse rates by simply saying that it's a reciprocal relationship. Let's have a look at it. If I want to write the equilibrium expression in the forward direction, then we're going to write something that looks like this. In the forward direction, denoted with an F, the equilibrium expression forward, products over reactants. In this case, the products are the NO2. So it's going to be NO2 cubed divided by N3O6. Okay? Now, if we want to get the reverse of this particular reaction, what we're going to do is essentially we're going to flip it over. So in this case, if I want to write this reaction in the reverse direction, in other words, I'm going in this direction, so N3O6 is going to be a product now. So what I've done is flip the equation over because I'm talking about it in a different direction. Products over reactants, still the same thing, products over reactants. In this case now it's going to be N3O6 over NO2 cubed. So basically all we done was we flipped this over to get the reverse. And you notice here how I've denoted this as equilibrium expression for the reverse direction. And what we're seeing is that it's a reciprocal relationship. We simply flipped it over. So whatever value we get for the forward direction, we simply say 1 divided by that value, and that'll give us the reverse value. Okay? So again, equilibrium depends on what direction we're going to be looking at. Now, to keep things simple, if they don't tell you they want you to write the reverse equilibrium expression, then we always assume for the forward direction as the reaction's written. So if we look at this reaction right here, and they want us to write an equilibrium expression, we would always write this one because we always write it assuming the forward direction. Okay? But sometimes they'll trick you and say we want the reverse equilibrium expression, in which case you have to, if you write it this way, make sure you flip it over to get the reverse, because it's a reciprocal relationship. Okay, here are some of the calculations that we would do with these questions then. Here's a typical chemical reaction. This is just like one of the first ones we did on the other page. In this case, they gave us some equilibrium values. They said, okay, the system's at equilibrium value. We want to verify the value of K, just to say that, are these concentrations the concentrations at equilibrium? So what we do is we would proceed to write this particular equilibrium system K. So we don't have to use iron because that's a solid. It's not included in equilibrium. And we don't have to use the iron oxide because that's also a solid. So the equilibrium expression is simply going to be K is products over reactants. And as we write this, it's going to be the concentration of hydrogen cubed divided by the concentration of water gas. Remember now, water is a gas, so we use it. And we would say, okay, we've given the values were given, and we plug them into our equation. Okay, so the concentration of hydrogen was given to be 0.190, so we put that in, we have to cube it. And then we divide that by the concentration of water gas, 0.0822, and cube that. Now if you're not sure how to use your calculators, then you would type in 0.190 to the power 3, and then divided by 0.0822 to the power 3, and you would get your answer. And the answer works out to be, if this is equilibrium, the answer should work out to be 12.3. Because what that's saying to us is that the concentrations at this temperature have reached their state of balance. All right, the rate of forward and reverse are equal, so the concentration should no longer be changing, and the level that there should be at 0.0822 for water and 0.190 for hydrogen if we are at that state of balance. And lo and behold, we do the calculations, and yes it is. We would round it to 3 significant digits here, and we get 12.3. And our conclusion would be then that, yeah, we're at equilibrium because the concentrations are now at their stable values. And that's what the equilibrium expression represents. It's telling us what are the stable values or the stable concentrations for the species involved. And in this case, we are at the state of equilibrium because we're at those stable values. If we were not at equilibrium, then we would get some other value for the equilibrium expression. And hence, we've quantified equilibrium. We now know where that balance should be. Okay, here's another reaction then. And in this case, we want to calculate the value of K this time. K is not given. We are saying that here are the stable values. The nitrogen, trinitrogen hexoxide is a concentration of 0.045, and the concentration of nitrogen dioxide is 0.030. So we're telling you that these guys are the equilibrium values. These are the values at when everything should be stable. And what I've done here is I've denoted this with a little e. Now this is going to have meaning later on. I've denoted this with a little e, saying, okay, these are the equilibrium values for these two species right here. So what we want to do is we want to be able to calculate the value of K. We have no idea what it is. We want to calculate it given the equilibrium values. So we simply proceed here by saying K is products over reactants. And in this case, we have both gases, so we have to use both things. So we would write this as the concentration of NO2 cubed divided by the concentration of N3O6. We would plug our equilibrium values in. There we go. So 0.0300 cubed divided by 0.0045. Careful not to mix up these numbers, products over reactants. Do our math on this with our calculator, and lo and behold, we get 6.03 times 10 to the minus 3. If you don't like that on your calculator, then you can change it to regular notation here. This is scientific. So negative 3 means we have to pull the decimal place 3 ways, 3 times that way. We get a little tiny number, negative 3. So we're pulling our decimal place this way. So 0.0060. Now, the reason we don't have a unit on this number, some people are saying, well, what's the unit for that? What should that be? Well, the equilibrium constant is going to be dependent on what's involved in equilibrium. In this case, it would be moles per liter is the concentration, moles cubed per liters cubed divided by moles per liter. So this guy would have a unit of moles squared per liter squared. Now if we looked at another particular reaction, like this guy over here, this guy is going to have moles per liter cubed divided by moles per liter cubed. So the units would actually cross out in this case, so it wouldn't have a unit. So rather than complicate things by putting units on these numbers, the units really don't have any meaning for us. It's the value or size of K that's going to be important. You know, whether it's greater than or less than 1 is what we're going to be looking at. We'll talk about that now in a few more minutes. But it's the size or the value of K that's important, not its unit. The unit really doesn't tell us anything, so that's why we would leave it out. Okay, here's another one. In this particular type of example, we give you the value of K. We're going to give you the concentration of one of these species. We want you to calculate the other. All right, so if we read the question, we're saying the equilibrium concentrations of hydrogen and iodine are both 0.0122. Okay, so the equilibrium value of hydrogen and iodine are both 0.0122. We want to calculate the molar concentration of hydrogen iodine at 700 degrees Kelvin, and we know what the equilibrium constant is at 700 Kelvin. It's given to us. So what we're going to do is proceed to do this question again, and we're looking at this and saying, okay, K is going to be products over reactants once again. So we would write the equilibrium expression for K, products over reactants. So it's going to be the hydrogen iodide squared divided by hydrogen times iodine. Let's put our values in. Okay, now in this particular case, we know what K is. It's 54.6. So we put that in. We don't know what hydrogen iodine is. It's X. It's unknown. So we would say X squared. And we know what these two values are. They're given right here. Okay, so we would proceed to do our calculations. Now in this particular case, we want to solve for X. So what we're going to do is simply cross multiply here. All right, to solve for X, so we're going to cross multiply these guys. So it's going to be 1 times X squared equals 54.6 times 0.0122 times 0.0122. So there we go. So we get something that looks like that. All right. Now what we do is we simply solve the value on the right-hand side and solve for X. So when we multiply all these numbers together, 54.6 times 0.0122 times 0.0122, we get 8.126 times 10 to the minus 3. And now on your calculator, you're going to hit the generally second function of squared to get the square root there. So we take the square root of that value. And what we end up with now is going to be a concentration, isn't it? We're trying to find the concentration of hydrogen iodide. So what we're going to end up with is 0.09014, and it's a concentration. So now we have to put a unit on it because it's moles per liter. And in this particular question, we're doing a whole bunch of multiplication and division. they gave us 3 significant digits in the question. All right, these 2 zeros are not significant because there's no number in front. The zeros are only serving to set the decimal place. So this particular question will have 3 significant digits. So the 4 will round down. The answer is 0.0901 moles per liter of hydrogen iodide. Okay, typical question you would get. This could be a multiple choice type question on a public exam. Rarely, you may see it on a long answer question, but we reserve the ice table questions for that usually. Okay, well, what is the meaning of K? In every single example we've been given, we've been getting different values of K, and we're saying that the unit doesn't mean anything. It's the number or the size of K that matters. Well, let's have a look at what K really represents to us. Okay, let's just black out some of this. All right, the meaning of K is dealt with on page 511 of your textbook. You may want to go and have a read on that. All right, what we're looking at is there's different situations for K. If K is less than 1, let's have a look at what K represents. We're saying that if K is less than 1, the equilibrium lies to the left, and we're saying the reactants are favored. Well, what does that mean, the reactants are favored? Well, if I do my equilibrium expression, K is products over reactants, and we're saying that the reactants are favored, the reactant concentration should be much larger than the products. So let's put in some hypothetical numbers. Let's say the reactants are 10 times the concentration of the products. So it's going to be 1 divided by 10. I get a value of 0.1. And what we're saying is that this value is less than 1. Now an easy way to remember this is saying, okay, if this is less than 1, look at the way that that little less than sign is pointing. It's pointing in that direction. So what it's telling me is that for this particular reaction, the reactants have a higher concentration because this guy's pointing in that direction. And graphically, we can look at this and say, okay, well, this is a situation where the reactants and products don't cross, because once we've achieved equilibrium, when the concentrations balance off, we're seeing that the reactant concentration is higher than the products. And every time the reactants are larger than the products, we're always going to be dividing by a bigger number. So we would always end up with a decimal place when the reactants are larger. Okay, so we can say then that the reactants are going to be much larger than the products. So if we look at this graphically, A, B, C, D, we can see that the concentration of A and B are much larger. So you can see that the equilibrium, the reverse reaction, is faster because it's pointing that way. And that's what that little less than sign is pointing to. So when K is less than 1, the reactants are favored. Now we look at this from the other perspective and say, okay, well, what does it happen when K is greater than 1? Okay, well, when K is greater than 1 this time, we're saying the products are going to be favored. And if the products are favored, that means at equilibrium, the product concentration is going to be larger than the reactant. So again, hypothetically, let's say that the product concentration is 10 times that of the reactants. So we're going to be dividing by a bigger number on top. And we're always going to get a value that's going to be greater than 1. We're never going to get a decimal because the top number is always going to be bigger than the bottom number. So in this case, K is always going to be greater than 1. Look at the way that that arrow is pointing. K is greater than 1. It's pointing in that direction. All right? If we look at this, the products are going to be greater than the reactants. So in this particular situation, the products end up being larger than the reactants. K is greater than 1. Okay, what does that look like graphically? Well, this is the situation where once we achieve equilibrium, the product concentrations now are much larger than the reactants. So P, the products, are always going to be bigger. So we're always going to get a value greater than 1. Okay. In terms of writing these values, K is always going to be larger than 1, so 1.5, 12, 10, 100, always values greater than 1. These numbers up here for K less than 1 are always going to be decimal places. You're never going to get a negative number, all right, because you're always going to get a number greater than 0. but it's going to be between 0 and 1. It's always going to be a decimal. So in these cases, we always get a decimal value when k is less than 1. And a nice way to look at this is we always get a negative exponent. So for these guys here, we're always going to get 10 to the negative exponent. These guys over here, we would usually get a positive exponent. 10 to the 1, 10 to the 2, 10 to the 3. Okay? And finally, we can say, well, what happens if the concentrations of products and reactants end up being equal? Well, that rarely happens, because remember, it's not the concentration of the products being equal to the reactants that makes it equilibrium. Remember, it's the rate of forward equaling the rate of reverse reaction. So you would rarely get a concentration set up where the concentrations would be the same on each side. And in this case, of course, this rarely ever happens. It's very difficult for me to even give you an example of a reaction system that has the products equal to the reactants. It rarely occurs. So you generally have a situation where it's going to be less than 1 or greater than 1. So if we go back and look at this particular calculation right here, we're saying, look, k is greater than 1. K, I'm just going to do this in a different color here. We'll look at this and say, k is much greater than 1. So what this is saying is that the products are favored. And is that the case? Well, look at the values. The reactants are 0.01. The product concentration ends up being 9 times bigger, 0.09. Does that make sense? Well, that's what we predicted. We said k is greater than 1, so the products are favored. We should get more product. We did. We got 9 times the amount of product. Okay, if we look over here, we're saying okay, now when we have exponents and whatnot, that starts to complicate the simplification, so we won't go on to that one. All right, but generally speaking, that's what we're looking at. Okay, now here's the last thing in this lesson. We want to be able to look at what's the effect of k, what's the effect of temperature on k, because we've talked about this all along and saying k stays the same as long as we have the same temperature. If we start fooling around with the value of k, or the value of temperature, then k changes as well. So that's the only thing that will cause k to change, is if we change the temperature. All right, that's a very important point. All right, I got a little footnote put by that. A change in temperature changes the value of k. No other disturbance has the effect on k. If I change the gas volume or the gas pressure, k stays the same. If I change the size of my container, k stays the same. The only thing that's going to change k is if I put it in a hot bath or cool it down, heat it up or cool it down, then k will change. So what we want to do is look at the effect of changing k. So if we look at this particular reaction here and saying, okay, sulfur trioxide plus 197 kilojoules of energy goes forward to produce sulfur trioxide and oxygen. What have I got down here? This should be sulfur dioxide. Sorry about that. Let me just fix that. So it's going to be SO2. Here we go. And the value of k for this reaction at standard temperature and pressure is 21.6. Okay? So the question would be, well, let's start manipulating the temperature here. So it says if the change in temperature causes the system to shift forward to produce more product, then k will increase. Well, what do we mean by that? Okay? If we look at this particular reaction and say, okay, let's cause this guy to shift forward. And in order to get this guy to shift forward, what we're going to do is increase the temperature. So let's say we increase the energy to, say, 300 kilojoules of energy. Le Chatelier's principle says that this reaction should shift forward to get rid of that excess energy. Now, by shifting forward, what's going to happen is the concentration of these guys on this side are going to go up. So the products are getting larger. And we know that as the top number gets bigger, then k is going to get bigger as well. All right, so what's happening here now is k is going to be directly proportional to whatever happens to the products. If products go up, k goes up, only with a temperature change. So at this new temperature, the products are going to be larger. It's going to be a larger number over a smaller number. Therefore, the result is going to be K is going to increase. And it makes sense because of this temperature change, we're getting more products. The value of K is going up. We can also look at this and say, well, what can we do to make this particular reaction go down? So we're saying, if we can make a change on this system to cause the reverse reaction to be favored, if we can make this reaction go in the reverse direction, then we're going to make the product smaller. We're going to make the reactants bigger. So we're just playing with the mathematics here, and we're saying, if we can look at this and if we can somehow make the reactants bigger, then what we're going to see is that K is going to drop. K is inversely proportional. K drops as the reactants goes up because we're going to be dividing by a much larger number. Right? Now what will cause this reaction up above to want to shift in the reverse direction? Well, let's just clear out the top reaction and say, all right, let's make this colder. Let's drop the temperature down or the energy down to 100 kilojoules. And what we're saying here with this guy is that Le Chatelier is saying, boy, this is too chilly. We need to shift in this direction now to replace this lost energy. In the process, the reactants go up and the products go down. And the effect of that, of course, is now we're dividing by a bigger number. We're going to end up getting a fraction, a decimal number. And therefore, anything that causes the reactants or any temperature change that will favor more reactants is going to cause K to get smaller. Now remember, I'm going to put a little note here, only because of temperature changes. Only when we have a change in temp. Okay, and I'll put a little green box around that because that's very important. If I had to change the concentration, pressure, volume, even though the reactants or products are going to go up or down because of that change, it's not going to change the size of K. K is going to have to readjust. The equilibrium is going to have to readjust to get back to that particular situation. Okay? There we go. Now, don't forget about our online tutoring. Don't forget about the online material that we have there. And if you have any questions on this, then don't forget to drop me a line in the discussion posting so I can help you answer your questions. And if you want some more work on these, of course, then make sure you consult your textbook here. And, of course, the answers are noted in your textbook. Give them a try. See what you can do. Bye.